Okay, excellent. All right, so our lecture for today has to do with, we have two topics to cover. One is looking at the difference between two population proportions. And the second one has to do with now introducing what we call multinomial analysis, where we are involved with distributions, multiple distributions involving proportions. So we're going to start off first by finishing off chapter 10. And that portion of chapter 10 deals with the difference between two population proportions. All right. So I have my iPad all set up already, and we can go into the lecture. So if you have, if you received my email today, you could actually go in and click on the lecture, which is PowerPoint chapter 10b, and follow along. Or you can just follow along and later on go and check out the PowerPoint notes that I shared with you a bit earlier. So what's involved with two population proportions? Why would we be interested in studying the difference between two proportions? That could be of interest to marketers. It could be of interest to pollsters. So for example, during an election, a political party might be interested in comparing is the level of support for that party in one province versus another. And so then one could ask the question, is there a difference between the level of support for that party in province A versus province B? So for example, Quebec versus Prince Edward Island, or British Columbia versus Saskatchewan. And we won't have the actual population proportions, in other words, the level of support for the entire population of each province, because we would have to actually ask every single person in each of these provinces whether or not they support the party. But instead, we could take samples. We could take a random sample from Saskatchewan, a random sample from British Columbia, and then look at the sample proportions and use that to then hypothesize or determine what we call an interval estimate, a confidence interval, for the difference between those two proportions. All right? So let's just familiarize ourselves with some of the notation, and it looks like this. So essentially, the population proportions would be for us P1 and P2. And of course, we want to hypothesize about P1 and P2, or we want to estimate the difference between P1 and P2. So those are our population proportions. Sample proportions then would be, if we take two random samples, one from each population, then we will get two sample proportions. We'll get a P bar 1 and a P bar 2 if we generate a random sample of N2 from one population and a sample N1 from another population. And then using that information, we want to see if we could draw some inference or a conclusion about those two population proportions. All right? So we're going to start off with a confidence interval for the difference between those two proportions. But we need two important pieces of information. If you may recall, I'll just go back slightly here. If you may recall, the interval estimate for a population parameter has three parts to it. If we're trying to estimate mu, let me just change the color of my pen here. Let's go green. So if we're trying to estimate mu, or we're trying to estimate mu1 minus mu2, or P1 minus P2, doesn't matter, any of those, we always need a point estimate plus or minus a margin of error. But you may recall that margin of error has two parts to it, a critical value times a standard error. All right? So basically point estimate plus or minus critical value times the standard error. And the critical value times the standard error is what gives us the margin of error. So if we want to estimate the difference between P1 and P2, then we need a point estimate. What's that point estimate? Well, that point estimate would be the sample values, P bar 1 minus P bar 2. And then what's the critical value? Well, we are still dealing with proportions, and we will assume that the sampling distribution of the sample proportions, or the difference between the proportions, is a normal distribution as long as we satisfy certain conditions. And what are those conditions? You remember the conditions for the binomial to be approximated by a normal distribution means that we have to take N1 P bar 1 must be greater than or equal to 5, and 2 P bar 2 must be greater than or equal to 5, but also N1 1 minus P bar 1 must also be greater than or equal to 5, and N2 1 minus P bar 2 must also be greater than or equal to 5. So those are conditions that we want to make sure that are satisfied. And then with those conditions satisfied, we could use a normal approximation to the binomial. So we would need a standard error. And what's the standard error? The critical value and then the standard error. Well, the critical value in this case would be Z, because we would use a normal distribution. But the standard error for P bar 1 minus P bar 2, the standard error is given by P bar 1 minus P bar 1 over N1 plus P bar 2 1 minus P bar 2 over N2. Now, if we had the population parameters, we would simply use P1 into 1 minus P1 over N1 plus P2 1 minus P2 over N2. But because we don't have the population parameters, we will use the sample values. And that's our best estimate, our best guess in this situation. So that's essentially what the confidence interval would look like. For the difference between two population proportions, it would be our point estimate right here, P bar 1 minus P bar 2, plus or minus Z. And the Z depends on the confidence level. So you know if it's a 90% confidence interval, it's 1.645. If it is a 95% confidence interval, it's 1.96, and so on. And then, of course, the standard error, which is right here. Standard error, critical value, and then point estimate, right? Standard error. Good. So if we have that, we could actually go ahead and do a confidence interval for the difference between population proportions. So we will see, here's, the standard error. Here is the expected value, or basically just saying that the mean of P bar 1 minus P bar 2 would be the same as the difference between the population proportions. And then we have our conditions that must be satisfied, as I've already mentioned. N1 P1 greater than or equal to 5, N1 P2, 1 minus P1 greater than or equal to 5, etc. N2 P2, and then N2 to 1 minus P2. But then we don't have population proportions. So we're going to have to use the sample values to achieve the same thing. We're going to test it out with sample values. All right? As long as they're satisfied, we're good to go. So we have our sampling distribution of P bar 1 minus P bar 2, which is a normal distribution. And so here is the interval estimate I just showed you early on. Our point estimate, which is here, our critical value, and that should not be equal here. That should actually be, that equal sign should not be there. It's this times the standard error right here. All right. Notice that we don't have P, but we have P bar. Why? Because we don't know the population proportions. If we knew it, then we wouldn't need it. So therefore, we would actually just use the sample values. So to do an example, let's take a look at an example. We have market research is conducting, market research associates is conducting research to evaluate the effectiveness of a client's new advertising campaign. Before the campaign, a telephone survey of 150 households, right, in a test market showed that 60 of them were aware of the client's product. So we're doing some product awareness, I guess, in this case. 60 out of 150, and that sounds like a proportion to me. The new campaign has been initiated with the TV and newspaper, and it's now running for 3 weeks. So a survey now, immediately after the new campaign, showed out of 120 people, showed 120 of 250 households are aware of the client's product. Does the data support the position that the advertising campaign has provided an increased awareness of the client's products? In other words, if we can kind of get a sense that the proportion afterwards is bigger than the proportion before, then we have evidence that the campaign has worked. So then in that case, what we would like to be able to show, if this is the proportion before and the proportion after, we would like to make sure that that difference between those two is positive. Because we're going to get a confidence interval for P1 minus P2, it means both limits must be positive. This must be positive, and this must be positive. Why? Because if the lower limit is positive and the upper limit is positive, then any value in that interval is also going to be positive. And if any value in that interval is positive, it means that P1 is bigger than P2. So actually, that's not what we're looking for. We want P2 to be larger than P1 if the company has now increased awareness. So in fact, ideally, what we're looking for is two negative values. In other words, this should be negative and negative. And if both limits are negative, then any value in the interval will be negative. And if any value in that interval is negative, it means P2 is the larger of the two. If I wanted to base my criteria on having positive limits for the interval, then I would have to take it as P2 minus P1. In which case, I want P2 to be larger than P1, so therefore I would want both limits to be positive, all right? Sorry. But if one is negative and the other one is positive, it means that it is possible in the interval, because between the negative value and the positive value, there is the value of 0, right? And so if it is possible that the difference between them can be 0, it means that we don't have clear evidence that one of them is bigger than the other. In other words, we have no clear evidence that the campaign has worked. So for us to make this claim that the campaign has improved level of awareness, we must be able to demonstrate that the proportion of people who are aware of the company's products after the campaign has now increased, right? Is now bigger than what it was before. We won't know exactly what it is. All we know is that there's a positive difference between the two. And so here's what we have. P1, population, proportion of households aware after the campaign. So you see how they define it? After the campaign, which doesn't seem to make sense. Really, P1 should be before and P2 should be after. But you see what it is, they want to keep that P1 minus P2. And if you're looking for positive difference, then P1 has to represent after and P2 have to represent before, which actually is not how our brain would work. Our brain would tell us P1, the first value is for before the campaign, second value is for after the campaign. But once you get your head around that, then you'll understand what they're doing. So you could see here that after the campaign, 120 out of 250. Before the campaign, 60 out of 150. So basically, after the campaign, the sample proportion was 48% and 40% before. So therefore, there is a sample difference of 8%. Now, that looks good, but that's just a single point estimate. How much confidence can we have in just a single value? So that's why we need the interval. So if we now go ahead and compute the interval, here's what we're going to see. We're going to see that we have our point estimate of 8%, 0.08. Because we want a 95% confidence interval, alpha is 0.05, therefore Z alpha over 2 is 0.025, which then gives us a Z value of 1.96. With that value of 1.96, now we have, and then we get the standard error right here. Notice what we're going to see. When we compute that, the interval is 0.08 plus or minus 0.10. The margin of error is actually bigger than the difference. So which means that when I add and subtract, I'm going to get a negative value. So as you could see from the interval, it goes to negative 0.02 to 0.18. So some people have a tendency to look at it and say, oh, but you have 0.18 is much bigger than 0.02. In other words, the positive part of the interval is a lot larger. So therefore, we could conclude that P1 is larger than P2. No, that's not true. All this interval represents is a range of values within which the actual difference lies. We don't know for sure, because remember, there's still a chance that the interval or the difference lies outside of that interval. But within that interval, we are 95% confident that the difference is in that interval. And that interval goes from negative 0.02. So if the difference happened to be negative 0.02, in other words, negative 2%, that means that the proportion who are aware before is actually larger. If it is 0.18, then that means after is larger. But what if it is 0? There is 0 in that interval. I mean, if you go from negative to positive, you have to cross the 0 point. So if the difference happens to be 0, that 0 point, then it means that the two of them are the same. So in that interval, there is a possibility that more people were aware before, or it has not changed, the same proportion are aware before and after, or more people are aware after. In which case, you cannot conclude, or you cannot say conclusively that that you have customers are more aware of the product. So that interval does not support the idea that more clients or customers or more households are aware of the company's products. So that's kind of how we would do this. Here's another example. If we're doing this, we have Forbes reports that women trust recommendations from Pinterest more than recommendations from any other social media platform. But does trust in Pinterest differ by gender? In other words, if we were looking at Pinterest alone, is there a difference between the level of trust of men versus women, right? So we have sample data, 150 women, 170 men. 117 women say they trust it, and 102 men say they trust Pinterest. So what is the point estimate of the proportion of women who trust recommendations on Pinterest? So that point estimate then would just simply be for women, so let's just put P bar W, it would be 117 over 150. We could figure that out. And for men, it would be 102 over 170. So those are the sample values. If we want to calculate that, we certainly can. If I grab my handy dandy calculator, 117 divided by 150 is 0.78. And 102 divided by 170 is 0.6. 0.6. So 60% for men, 78% for women. That looks pretty big, you know? So we've just calculated women, men. Now if we want to find a 95% confidence interval for the proportion, the difference between the proportion of women and men who trust recommendations on Pinterest, then all we need to do is simply use our formula, right? So what was our formula again? Confidence interval. Let's see what the yellow turns out to be. Would be P bar 1 minus P bar 2. Wow, this looks quite nice and rich. Sorry, let's just do women. Let's do it properly. Women and men. Plus or minus Z alpha over 2 and into the square root of P bar women, 1 minus P bar women over the sample size of women plus P bar men, 1 minus P bar men over the sample size for men. So that's precisely what we would have. So it'd be like 0.78 minus 0.6 plus or minus for 95% confidence interval, 1.96. And then we would have 0.78 times 0.22 over 150 plus 0.6 times 0.4 over 170. When we calculate that, then we should have what those values are. Let's see if I could grab that information for you. It was question number 31. So here we go. If we look at the computations right here. So you just saw what I did. So here are your answers A and B. And then with part C, we would have the difference between those two values, which is 0.78 minus 0.6, which is 0.18. That is the point estimate. 1.96 is our Z value. And here's the standard error. So you will end up getting 0.18 plus or minus 0.0991, right? 0.18 plus or minus 0.0991, which basically would give us P for women minus P for men lies between, if we go 9 and 8, 27, 27.2791, and that's 9. Oh, and 10 from 18 is 8.08. So 0.0809, which is basically, if we put it in percentages, that's 8.09%. PW minus PM to 27.91%. So what is that telling us? We are 95% confident that the difference between women and men who trust Pinterest lies somewhere between 8% and 28%. That's a huge gap there, a huge interval. But that's kind of where that lies, all right? And both values are positive. So because both values are positive, for you to get a positive difference, PW must be larger. PW has to be larger. So if PW is larger, that means the proportion of women who trust Pinterest versus men is actually larger. So more women are trusting Pinterest than men. Now remember, this is a confidence interval. It's a 95% confidence interval. And so with a 95% confidence interval, excuse me. So yes, so we have it just threw me off there. So basically, we have a 95% confidence interval, which means that there's a 5% chance we can be wrong. All right? So that 5% chance that we can be wrong, we have to basically be aware of that. But the reality is that we are 95% confident that that is the case. Okay? All right. Great. So that's confidence interval involving difference between two population proportions. If we now move to hypothesis testing, what we now need to know for hypothesis test is what is a test statistic. Remember that we're still dealing with the same 5 steps where we state the hypothesis, we state the test statistic, the decision rule, we collect the data, compute the value of the test statistic, and then we measure that to see how strong it is to support the claim that we're making. If you look, we have the same 3 cases where in HA, we are attempting to show P1 minus P2 is less than 0, which means that there's been a decrease. If P1 is before P2 is after, or something like that. If we're looking at P1 minus P2 greater than 0, that means we're expecting P1 to be greater than P2. And then if we are looking at simply that there's been a change between the proportions, then it will be P1 minus P2 is not equal to 0. Always remember that the equal sign must be in the null hypothesis. So greater than or equal to, less than or equal to, or equal to must be in the null hypothesis, because we have to assume a value for that difference. The null hypothesis has to assume a value. So that's why I need the equal sign in there. If we had this as our null hypothesis, and we simply say P1 minus P2 is less than 0, which value do you set it to? We don't know. So we need to be able to set HO to a particular value, and what we call is that we set it at the boundary. So since we know it's supposed to be greater than or equal to 0, we say, why don't we set it to 0 at the boundary, and then do the tests at that boundary, okay? So we have these 3 different scenarios. And then, of course, the standard error is going to be a little interesting, a little different, because with the formula that I showed you earlier for the standard error, it looked like this. P bar 1 minus P bar 1 over N1 plus P bar 2 1 minus P bar 2 over N2. So that's kind of what I showed you earlier as the standard error. But you know, looks a little different. Now, something is missing here in my formula. So the book has an error right here. Either the book or the PowerPoint notes produced by the authors. There's supposed to be a bar missing. Now, if you look at that, you'll see, why is there this difference? Why don't we have the P bar 1 and P bar 2 and so on in the formula? And let me explain why. If we are testing a hypothesis, in the null hypothesis, HO, we will assume P1 minus P2 is equal to 0. All right? That's what we're going to assume. We're going to set the value of P1 minus P2 to 0 to do the test. That means from this formula, we are essentially saying P1 is equal to P2. We are saying that they're the same. If we're saying P1 is equal to P2, we cannot use 2 different estimates. In other words, when we have P bar 1 here and P bar 2 here, the chances are those 2 sample proportions are not the same. Excuse me. So if those 2 sample proportions are not the same, so for example, we had 0.6 and 0.78, they're not the same, yet we're saying P1 is equal to P2. So that means we want an estimate such that P bar 1 and P bar 2 should be equal to the same value, P bar. So we cannot estimate the same thing with two different values. We need one value. So because the sample proportions might actually be different from each other, we blend them, we combine them using this formula. We combine them to create a single estimate, so that we have to find a way to blend that 0.78 and that 0.6 to create a single estimate. So that's one formula right here to do it, which is we basically are going to take the sample from N1 times the proportion. In essence, that really just gives us the observations that we had, X1. And then this one will give us the observations from sample 2, X2. So we could also write this as P bar is equal to X1 plus X2 over N1 plus N2. When I say X, I mean the number of observations. So for example, I believe if we go back to our example right here with the proportions, I think it was what, women and men, 117 and 102. So if I use that formula, P women, bar women was 117 over 150. P bar men was equal to 102 over 170. And you know that was 0.6 and that was 0.78. So as you could see, those two things are not the same. So how can we create a single estimate? We will create P bar by joining that 117. So we call that X for women plus X for men. That's the number of observations over N women plus N men, which basically would be the 117 plus 102 over 150 plus 170. That's how we would get that estimate. And I believe that's 219 over 320. 219 divided by 320. 0.6844. So that would be our single estimate when we blend the 0.78 and the 0.6. Now, the formula that was shown to you a little earlier, this formula right here, I want you to see that it's actually the same thing. If you look at it, P bar, we said is equal to N1, in this case, N women. Oh, sorry, let's fix that up. N women times P bar women plus N men times P bar men over N women plus N men. Well, what is the N for women? It's the 150 times P bar. Well, what's the P bar? 0.78. If I multiply that, I will get the same. I would get the same 117. That's exactly what I'm going to get, 117. In other words, if you look here, you'll see that 117 is, if we cross multiply, is 150 times 0.78. So that will actually equal to 117, which basically brings us back to what I had up here, which is the number of observations. All right, this piece right here was 170 men times the proportion, which was 0.6. Well, that's going to give me the 102. All right. So the two formulas are identical. You would use this formula if you did not have the actual number of observations, but you just had a sample size and a sample proportion. You use this formula when you have the sample size and the number of observations, right? But they give you the same thing. They will give you exactly the same thing, all right? So that's that. Let us take a look at, so what happens now is that once we get that P bar estimate, we just substitute, let's go back here. Once we get P bar, we substitute everywhere that we have P bar 1, we'll replace it by P bar. and P bar 2 will replace it by P bar. Let me show you what I mean by that. So if I take my standard error to be P bar W 1 minus P bar W over NW plus P bar M 1 minus P bar M over NM, right? That's the standard error. Remember that we cannot use two different sample values to estimate a same value. So what happens now is that we've calculated P bar, which is obtained by blending the two. And now if I just erase these, I replace everywhere I have P bar W, for example, I would replace it by P bar, right? The single estimate. And P bar M, I'll replace it by P bar. So it becomes, so those values are now replaced by the common value. And then now I could factor that out because I do have the same, I do have P bar into 1 minus P bar on both of those. Those two are the same. So then I could factor out P bar, 1 minus P bar, into 1 over NW, 1 over NM, and then take the square root of that. And that would be my standard error, okay? So that's kind of what you see right here as the standard error in the denominator. And then remember now with the test statistic, the test statistic initially would have been sample value, P bar W minus P bar M minus PW minus PM, right? That's population, so sample minus population over the standard error, which is this piece that we have up here. But in HO, we will be saying PW minus PM is equal to 0. If we're going to say that in HO, it means that this is equal to 0. If that is, if PW minus PM is equal to 0 from the null hypothesis, then we could get rid of it. And if we get rid of it, as you could see, by getting rid of it because it's 0, you're left with that piece right here, which is what you've seen up here. And then, of course, over the standard error. So that's kind of how we end up with this test statistic, okay? All right, let's do an example now. So now that you understand the test statistic, all the things that we've done already in hypothesis testing just applies. The only thing is just a matter of what is the appropriate test statistic right there. So this is a case where we have the same problem with the campaign. So we're being asked to, can we conclude using a 5% level of significance that the proportion of households aware of the client's products increased after the new product advertising? If it increased, that means the proportion after must be bigger than the proportion before. Now remember the way in which they've defined the proportions, P1 is after and P2 is before. So P1 minus P2 should be greater than 0 if they increase the proportion of households aware of their product. So that should be our research hypothesis, and therefore the null is exactly opposite. All right? So that's step 1. Step 2, level of significance. The level of significance helps us to determine the decision rule. If we're applying the p-value approach, then we must make sure that p-value is less than alpha. But if it is the critical value approach, we need to find that critical Z value. But what is that critical Z value? That critical Z value for us will depend if it's a one-tailed test or a two-tailed test. If we go back to the hypotheses, we will see we have a directional arrow. We want P1 minus P2 to be greater than 0. not equal to. If it was not equal to, then it would be a two-tailed test. But we want it to be greater than 0. So that means that it's a one-tailed test. All right. Since it is a one-tailed test, then in that case, we're looking at the upper tail, and that area is alpha, which is 0.05. If that area is alpha 0.05, the Z critical is 1.645. If you don't believe me, you could just go to the table and then find 0.05 in the tail, or if you're looking at the dotted region, that would be 0.95, and you get Z is equal to 1.64, 1.65. You go in the middle, you get 1.645. All right, so that would be our critical value. So if our Z statistic or our test statistic is greater than 1.645, we will have evidence to support us. All right. Compute the value of the test statistic. We calculated, here's our sample proportion. That's from the data obtained earlier. And then if we look here, we compute the standard error. It's 0.0514. We have what P bar is. Now if we compute the Z value, which is the difference between the sample proportions, and we divide by the standard error, we'll get 1.56. Remember, this question here has to do with the households, not the one I just did about women and Pinterest, just the households. So if that's the case right here, you could see that 1.56 is smaller than 1.645, so we will not reject the null hypothesis. That means we will not conclude that the marketing campaign was better. And you may recall that we had a negative difference and a positive difference in the intervals. If I go back to that, for that very same problem, we were not able to show this is it right here. Remember, we found negative 0.02 to positive 0.18. That was such that we could not conclude the campaign was successful. Well, it just turns out that the hypothesis test is actually telling us the same thing. So because our test statistic is going to be smaller than 1.645, we will not have enough evidence. So let's compute the p-value. P-value, by definition, now would be the probability of Z being greater than or equal to 1.56. When we compute that, it turns out that it is 0.0594. So again, how do we find that? We look up the 1.56 in the table, the Z table, and then we should be able to get this area right here. I could certainly show you that if you would like, so I'm going to just stop sharing this for a brief moment, and then I'm going to share something new. Let's see, where are my tables? There we go. So Z, we want positive 1.56. So if we look up 1.56, we will get the area to the left, right? But remember, the area associated with negative 1.56 is exactly the same area. So why not, since we want the area in the tail, why don't we look up 1.56 over here? 1.56 right here. So 1.56 gives us 0.0594. That's this area, which basically is the same area up here. So that's how we got the 0.0594 as the p-value. It's a one-tailed test, so therefore that area is just the p-value. You don't have to multiply it by 2. Stop that, share. And let's go to back to my iPad. Okay, so we're back here. All right, so good. So we can see now the p-value is actually larger than 5%. So since that p-value is larger than 5%, we therefore cannot conclude that we have enough evidence. So, because remember the rule is that the p-value must be smaller than alpha. In this case, alpha is 5%, but the p-value is 5.94%, in which case then we would have to come to this conclusion right here. Because p-value is greater than 5%, we cannot reject HO, therefore we cannot conclude that the proportion of households aware of the client's products increased after the new campaign. So that is consistent with the analysis that we did when we did the confidence interval. And that makes sense. Typically, you want those two things to be the same, all right? And I believe that that will cover up for us that covers for us dealing with two population proportions, both confidence intervals and hypothesis testing. This next page I'm just showing you here is looking at it in terms of the critical value approach. This approach before that was the p-value approach, where you compare p-values, but now we will compare the critical value with the test statistic. And remember, we computed that the critical value is 1.645, test statistic was 1.56. So as you can see, the test statistic is smaller than the critical value. We cannot reject HO. So we get exactly the same conclusion. And if you got something different, then you know that you have actually made a mistake, all right? Good. There's a problem here that I'm going to let you work this particular problem by yourself. Now that you've seen the confidence interval, and then you've seen the test statistic for hypothesis testing involving two population proportions, then you should be able to work this problem. I'll just quickly go through it with you, which basically says the ADECO Workplace Insight Survey sampled men and women workers and asked if they expected to get a raise or promotion this year. Suppose the survey sampled 200 men and 200 women, so same sample size, so it's balanced. If 104 of the men replied yes and 74% of the women replied yes, are the results statistically significant that you could conclude a greater proportion of men are expecting to get a raise this year? So if we actually write our population proportions as PM for men and PW for women, then what we have is that we will be looking for, in our alternate hypothesis, PM minus PW is greater than 0. That means the proportion of men should be larger than the proportion of women. All right? So that's kind of what we'll be expecting to see in that situation. So, excuse me, that's the first thing. The other thing, of course, is we could get the sample proportions by simply dividing those numbers. So 104 over 200, that gives us 0.52, 52% for men, and then 0.74 divided by 200, 74 is 37, 37% for women. That's a big difference. 52% of in terms of the sample for men, P bar M, and P bar W for women was 37%. So you can see in terms of the sample values that a higher percentage of men already think that they're going to get a higher salary. So we've computed A and B by doing that. And then to do the hypothesis test, you would simply need to frame the hypotheses, which is basically the null hypothesis saying that either they get the same or that women get a higher percentage. But then HA, which is our alternate hypothesis, our research hypothesis, would state that the proportion for men would be larger than the proportion for women. And then the level of significance is 1%. This is a one-tailed test because we want proportion of men larger than that of women. So with 1% in the tail, the critical value will be Z is equal to 2.33. You could go and figure that out with 1% in the tail. So the p-value approach is either the p-value being less than 1% or the critical value approach that the test statistic is larger than 2.33. All you now need to do is to go ahead and compute the test statistic. And remember, in this case, you're going to have to blend the two sample proportions because 0.52 and 0.37 are very different. And they're supposed to be estimating the same thing because in a null hypothesis, we will assume that the proportions are the same. So you're going to have to compute, what is it, 74 and 104? You're going to have to say P bar is equal to 74 plus 104 over 200 plus 200, which basically is 178 over 400, right? 4 fours are 16, 16 and 17, 4 into 18, 4 fours are 16, and 2, 18, 4 into 20 is 5.445. That would be your sample proportion, your pool proportion that you would use, okay? You could do the rest of the computation and determine whether or not you have the support for the alternate hypothesis. And I suspect you will because that sample proportion is huge. The gap between them, 0.52 and 0.37. That's approximately 15% gap, 0.52, 0.37, 0.15. That's a 15% gap. That's huge. Okay, so that brings us to the end of our segment on difference between population proportions. All right, in fact, here is the answer. So I'm showing it to you, but I would like you to work it yourself. And when you compute it, you could compare it to that. And you could see here that the Z value is 3.02. Remember the critical value we said was 2.33. This is going to be greater than 2.33. So we'll reject the null hypothesis and conclude there is a difference, there's a significant difference between proportion of men and women who believe that they will get a raise. And that's interesting because somehow men always feel that they will get what they want, and women tend to be a little more reserved about those, it seems like. At least that's what the data seem to be suggesting. Maybe perhaps because there's bias in society that, because we know that there's all kinds of studies that have shown that women don't get the same pay as men. Women don't get the same opportunities for promotion as men. So one of the societal ills that we have to address as we go out and venture out into the world and try to change things and make things better. So making sure that we have equal work for equal pay and that men and women are equally represented and have equal opportunities. Those are very important values that we have to have as people who are going to attempt to influence business practice, okay? Good, so any questions for me before we touch on chapter 12, which is a fun chapter, I believe. Any questions for me, folks? We have a couple folks out there who are with me tonight. Was I clear tonight? Hello?
Yeah, you're clear.
Okay, good. All right. So we move to chapter 12 then. Let me close this.
At this point in time, I'm just getting onto chapter 13. Is that am I ahead or just on track?
No, you if you're on chapter 15, you're ahead.
No, 13. 13.
13 deals with analysis of variance, correct?
Correct.
Yes, no, you are ahead of us. That's our next class.
That's our next class? Okay.
Yes, so you are actually ahead. So we're doing chapter 12 today. Basically, if we look at the outline, And we're supposed to be doing 10.3, I believe it is.
Yeah.
And
And
and chapter 12.
I just had a question. What was the average for the quiz?
Oh, okay.
Do you have the class average for the quiz?
I do have an average for the quiz. It was 60 something percent. Let me just see
Okay.
here.
I was just curious.
Yeah, I was hoping that it would have been higher.
Yeah.
But one of the things I've been noticing is that I know that we have the video lectures and everything, but the numbers of students who are attending the online sessions have been very small. So
Right.
I'm not sure if that's because people figured they could figure it out on their own, because
Yes.
with the videos and MindTap giving you examples, so they're just working on, but they're not coming here at least to get a additional explanation and so forth. But you know, a number of
Mm-hmm.
students have good marks, and then you do have some, unfortunately, that are not as strong as I would
Right.
like to see. So I'm hoping with the second test, things will.
Okay.
And then I'm actually now offering, so on Thursday for an hour, 7 to 8, if people have questions. So this is the lecture time. Usually after
Okay.
the 2 hours, we kind of tired, so kind of watching the computer screen.
Yeah.
And but certainly Thursday 1 hour for if people have questions prior to the assignment, prior to the test, and that sort of stuff like that. So hopefully,
Okay. Good. That's good to know.
okay, all right,
Yep.
no problem. Good,
Sorry. Continue.
that's fine. So now let's go to chapter 12. I am going to just bring up my next chapter. And I'm going to use, this time I'm going to use a green background. Let's see here. Yeah, let's go with green. And then we are going to bring in chapter 12. I'm just bringing in my chapter right here. Bear with me. From here. And I'm looking for chapter 12. Where is it? Here we go. All right. So I shared a link today in an email that basically gave you guys access to the PowerPoint notes for the course. So and I don't think that I had shared that before. So at least you guys would have access to that. Let's see here. All right. So we want to now get into, we are now venturing into beyond two populations. So this is interesting now. So far, if we go back a little bit, when we started chapter 7, chapter 8, we were dealing with single population problems. Chapter 7, 8, and 9, I believe it was. So we dealt with confidence interval for the population mean, confidence interval for proportions, sigma known, sigma unknown, and we were looking at a single population where we were sampling from, say, a population of students, a population of businesses, and so on. And we were just dealing with a single population. Then we now expanded to 2, where we said, okay, let's look at difference between population means. So we had a confidence interval for difference between population means. We had hypothesis testing. And then we went into confidence intervals, which is what we just finished, for difference between population proportions, and hypothesis testing for difference between population proportions. Now we are venturing into 3 or more populations, and that takes care of everything. 3 or more populations, and we will look at that in terms of comparing population means and also looking at population proportions. So chapter 12 deals with proportions And then chapter 13 deals with the means, where you get into analysis of variance, like the gentleman who just asked me a little earlier. So here are three situations for us where we will look at data that comes from three or more populations, multiple populations, and we want to do tests, certain tests, hypothesis testing, with these three or more populations. So there are three cases that we tend to look at. The first one is called testing for equality of three or more population proportions. So let's say, for example, I'll give you an example of that. What if we believe that the proportion of students who sign up for a major in science, a major in business, a major in arts and social sciences, what if we believe that the proportions are the same, right? If we believe those proportions are the same, then we could actually test a hypothesis around that. So that's an example of the first case right here, which is testing for equality of proportions, three or more proportions, right? So I'm saying the same proportion of students who sign up for these different majors. Or we could say that if we were looking at the percentage of students who get an A in the exams, the proportion is the same for science as it is for business, as it is for arts, right? So someone say, oh, no, it's easier to get an A in arts and social sciences. Well, so what proportion of students get an A in arts and social sciences? Oh, 40%. What's it in business? Oh, 32%. What's it in science? 25%. We say, oh, those don't seem like they're equal. So we could actually test whether or not the proportions are equal. And we would have to gather a random sample of students from science, random sample from business, a random sample from arts and social sciences, and then see what percentage of them actually got an A in their courses, and see if those proportions happen to be the same. So that's one example. The second case, which we call the test of independence, is a case involving proportional data that has to do with proportions, but we want to test whether or not two categorical variables, and I will show you examples of that shortly. Two categorical variables are independent of each other. In other words, let me see if I can give you an example of that. What if I took men and women? So we just did, so gender. So one categorical variable is what's your gender? And then what if I ask you, what's your most favorite form of entertainment? People could say movies, going to concerts, playing games, board games, or whatever it is. We could come up with different forms of entertainment, skydiving, but let's just say we picked about 3 or 4 different types. So in that case, what we will do is we will have these two categorical variables, the type of games, so we didn't put in categories, computer-based games, physical-based games, like paper-based games like Monopoly cards and so on. So if we use those as the categories there, under the types of games, and then the gender, we could actually test whether or not gender and the preference for a type of game are related. Or we could even look at things like this: football, basketball, and baseball. 3 types of sports and gender. Is there a relationship between those? Are they independent or are they related? And people in marketing usually want to know some of those things, right? In particular. The last one is what we call a goodness of fit test. And the goodness of fit test, usually we would state a distribution ahead of time. We'll say, we believe that 20% of students, 30% of students go into business, 20% go into science, and then say 50% go into arts and social sciences. Those are these. So in other words, we will have a distribution for the different proportions. And then now we say, that's what we believe. So can you look at some data and tell me if from the data that distribution is in fact the right fit for this data. So I would have to take a random sample of students, divide it up into the three different categories, and say, oh, what proportion in my sample actually are in science? What proportion is actually in business? What proportion is actually in social sciences? And see if those sample proportions are similar to the population proportions that we're predicting, that we believe. And if they are pretty much the same, then we say then that's a good fit between the distribution that we stipulated and the sample data. So they seem to be a good fit for this distribution. But if they're different, then we say that we don't have a good fit. All right. So those are the three categories. So let's go through. First, there are some examples that are already worked for us, and then I will attempt to do one of them. Those problems can be a little bit. They're not difficult, but they do have a fair number of computations to do. So I think, but the computations are very similar for all three. But you just need to understand the different contexts for the three of them. So I will go through one of them, an actual example, but in the PowerPoint slides, which you have access to, you will see the sample. So I'll go through the examples first that they provided, and then I'm going to work one through, okay? So let's start off with, we need some notation. All right. So a couple of things that we need to know about. One is that we still, because we deal with proportions, and then how does one recognize when a problem has to do with proportions? Usually the data is obtained by counting. So if I counted how many students go into science, how many students go into social sciences, and I have a big total, I could express those numbers as a proportion or a fraction of the total. That's how we identify proportions, right? So PI would just be the proportion from population I, PI, proportions. And we would want to keep in mind that, as I've already mentioned, that we recognize proportional data that has to do with proportions by looking at the fact that we obtain it through a counting process. If we're going to look at the very first case of testing of equality of proportions, then essentially what we're going to state in the null hypothesis is that the proportions for the different populations are the same versus they are not the same. That's as simple as it is. So if I had three population proportions, and I'm just looking for my pen, what did I do with it? Uh-oh. Where did it go? Oh, here we go. So it would look something like this. So we would say HO, HA. So typically we would write something like P1 is equal to P2 is equal to P3 is equal to PK. Because remember we say three or more populations. So that's what the null hypothesis would state. And then we want at least one of those to be different, but we don't know which one. So we just simply say at least one population proportion is different. All right? Because we don't know exactly which one. So or in other words, we could say not all the population proportions are the same. So we certainly can say that. So here's an example that will kind of help to make it clear for us. We have an area called Finger Lake. So Finger Lake Homes. So Finger Lake Homes manufactures, so not an area, a company. Finger Lake Homes manufactures 3 models of prefabricated homes, a 2-story colonial, a log cabin, and an A-frame. To help in product line planning, management would like to compare the customer satisfaction of the 3 styles of homes. Proportion P1 is the proportion who would likely repurchase a colonial home. 2 proportion likely to repurchase a log cabin, and a proportion likely to repurchase an A-frame. So we begin by taking a sample from each of them, and we would have the following data. So the data looks something like this. So essentially, if we look at this data, we have the different types of homes: colonial, log, A-frame, and likely to repurchase. And the idea is, the question that we're asking is, are the purchasers, or are people equally likely to purchase these homes? In other words, the likelihood of repurchasing of a colonial home is the same as the likelihood of repurchasing a log home versus an A-frame home. We're asking, are those proportions the same? So likely to repurchase versus, okay, so yes or no. So out of the 135 people who bought colonial homes, 97% of them, sorry, not percent, said that they would repurchase. If I calculate what that is as a proportion, 97 divided by 135, that's about 72%. 0.185. Something like that. 83 out of 101. 83 divided by 101. That's 0.822. So if you look at this sample estimate is 71% or 72%. This is 82%. Let's see, 80 over 124. That's 60.645. 0.645. So I'm just basically computing the proportion of people that say yes, they would likely repurchase that kind of home. And so if you look at those three proportions, right, they look fairly different. And we're asking the question, are those different, or do we have equality of proportions? So we will assume that they are equal and see if the evidence is strong enough that they differ from each other. All right? So how do we approach this problem? So to approach this problem, one of the things we have to do is we're going to have to calculate. So let's just do some labeling right here. We have two rows in this problem right here. So we'll refer to those as rows, of course, and then we have three columns. And I'll come back to that later. So we'll call the columns J, we call the rows I. We're going to need some notation. Those values that we have here, the 80 and the 83 and the 97 and so on, we're going to refer to them as Fij, observed frequencies. So that's what we observe. In other words, we took a sample of 360 homes, and that's how it broke down. It broke down, of the 360 homes, 135 of them were colonial. 97 people said, yes, we're going to repurchase that. 38 said, I don't think so. So we break it down that way. So that's what we observed in the sample of 360. However, there is something called an expected frequency. And the expected frequency is based on the null hypothesis. If we assume that people are equally likely to repurchase for the three categories of homes, then what should we have expected in the 360? What should we have expected? So we need to calculate that. We need to find a way to calculate that, and we will refer to those as EIJ, the expected frequencies. And the logic behind the analysis we're about to do for all those three things I mentioned to you earlier, test of independence, goodness of fit test, and equality of proportions, the analysis is identical, but they're just different contexts. What we have to now determine is how different are your expected frequencies from your observed frequencies. Now, in a previous book, we used to use E and O. O for observed, E for expected. But this textbook uses E for expected, F for observed. So, of course, if we know that these are the frequencies that we expect, if HO is true, and that's what we observe, if those two are very close together, then we cannot reject HO. That makes sense, right? It's kind of like this. If I said to my kid, I expect you to spend, I'm going to send you to the fair, I expect you to spend no more than $50, all right? Around $50, in that ballpark. And then the kid turns around and spends $52, $51. Well, you'll say, okay, you know, there's no real big violation there because what was actually spent, the observed, basically what, compared to what you expected, were fairly close together. But then if the kid spends $150, right? But I expected him to spend 50, there's a huge violation there. There's a big gap between what was expected and what was observed. So it's the same idea. If what I observe now, my F value, my frequencies, my observed frequencies, is very different from what I expect, then it means that HO cannot be true. Yeah? HO cannot be true. So the hypothesis that I'm testing in the example I gave you earlier with my kid is really about compliance. So my child is compliant versus my child is not compliant. So if my child spends $52 and I told him that they should spend 50, and I'm going to say that gap between those two is not so large that I would say that that child is a non-compliant child. But if they spend $150, I'm saying, whoa, that child paid no attention to me whatsoever. I'll reject the idea of them being compliant and conclude that they're not compliant. So it's the same idea. So if you understand that logic and that principle, that is what all these problems are about. It's about calculating an expected frequency based on the null hypothesis and comparing it to what we have in the data and seeing if those two are far apart. If they're far apart, then we have to reject the null hypothesis. If they're not far apart, then we don't reject the null hypothesis. It means now we're going to need a new distribution, which I'll introduce you to, called a chi-square distribution. But before we come to that, let's continue to get, let me see if it's over here. Yes, here it is right here. So how do we calculate the expected frequencies? The formula for expected frequencies, and that is the same for all three of them, EIJ is the row total times the column total divided by the overall total. Row I total, column total. Let's see what that looks like. I'm going to just separate that out for you slightly to look like this. Row over the total times the column. I'm going to just write it out like this for a little bit, and let's see why I did that, to see if we can understand those expected frequencies. So let's go back here and look at the row total. So my row total over the overall total, so 260 over 360, what is that telling me? That's just telling me the proportion of people. So by lumping everybody together, 260 people out of 360 said that they will repurchase, right? So in essence, the probability or the chance of somebody repurchasing is 260. I'm going to divide 260 divided by 360 is about 72%. It's about a 72% chance that somebody will repurchase. Well, so if we consider 135 homes that are colonial, how many of them, or how many people do we expect to repurchase? Well, we must multiply the 135 by the 0.72. That's about 100 and, sorry, let me just see. Oh, sorry, I divided wrong. Better just do this again. So it's 135 multiplied by 0.72. So I would expect about 97.2 individuals. So you're going to get fractions. 97.2 people to say that they will repurchase a colonial home. Let's see what it would be for log. So remember, 260 overall out of 360 said they're going to repurchase. So we're going to use that as our estimate, which is 0.72 of somebody actually repurchasing. So if you had 101 people bought a log home, and about the average is 72% of people will repurchase. Let's multiply that by 0.72. So that's 72.7 people would likely repurchase a log home. But look at our observed frequency. 83 people said that they would actually repurchase. So you're noticing that based on what we expect is 72.7 individuals saying, who bought a log home saying that they will repurchase, but somehow it's actually 83. It's bigger. What we observed, the number of people we counted was 83 out of 100. So that's more people than what we expect, which is a good thing. Let's see, 260 times 120, 72% of 124 for A-frames. 0.72 times 124. That's 89.28. So we expect about 90 people who purchase A-frames out of the 124 to say that they would have repurchased. So that's based on assuming that the proportions are equal. But instead we got 80, fewer, a little less, right? So 83 is a lot more than 72. And then we have 80 is a little less than 89. So the numbers are lining up a kind of way, but we're not exactly sure. So we need something, we need a systematic way of testing now that the difference between those two. But I want you to get a sense of how we calculate what is expected. So what we're saying is that the likelihood of repurchase based on grouping everybody together is 72%, which is the 260 over 360. And now I take that 72% and I multiply it by the 135, the 101, the 124. Well, that's actually what I've done is I've taken the row total divided by the overall total and multiplied it by the column totals. And that's where we get this formula right here. Row total times column total over this. And I wanted to put it this way because that was the 0.722 that I got. And for example, for the colonials, I had to multiply it by 135 to get how many of those people would actually I expect to repurchase. All right. So that's the formula: row total, column total over the grand total or the total sample size. So we have to actually do this for all of them. And those are the values that we would get. You see, I started calculating them for you up here. And then if you compare that, look at that, 97.5, 72.9, 89.5, etc. If we go back here, 97, 83, 80, how different are those numbers? We need a way to measure that. So here's the next thing that we need. We need this formula right here. This formula is called a chi-squared formula. It allows us now to measure just how different those two sets of numbers are, the expected frequencies and the observed frequencies. So we actually calculated using this formula. We take the observed frequency minus the expected frequency, we square it, and we divide it by the expected frequency. We call that a chi-squared measure. And the distribution kind of looks almost like something like this. It's not symmetrical. Something like that. It does not go below 0. There's no negative values in that because we're squaring the top, right? So it goes from 0 to infinity. And we refer to that as a chi-square. Chi-square distribution. Okay? So chi-square. Not chai or chi, but chi. Greek letter chi. It looks like an X, but it's not quite an X. It's an X with some little curves to it. Okay, so now that we have that, what does that distribution look like? It actually has a degrees of freedom, just like the T distribution, and it has area in the tail. So if you have the area alpha, this become chi-squared critical, or chi-squared alpha, and then we need degrees of freedom. The degrees of freedom in this case is k minus 1, which is the number of populations that we have. For this problem, we have 3 populations, so 3 minus 1 is 2. All right? So just k minus 1. And we actually treat it just like the T distribution. So with this problem now, here's what we would have to do. For every cell, let me go back here. For every cell in the table, we're going to have to calculate the difference between the expected value and the observed value, and then compute the chi-square. In other words, we have to calculate this thing right here. F minus E squared over E, adding them all up. So we're going to actually do this for each ij. For each cell, we have to do this. So for example, the first one would be 97 minus 97.5 squared over 97 plus, and then we got to do it for the next one, which I believe was I think the observed frequency was 83. Oh, yeah, 83. So now we have to take, next one is 83 minus 72.94 squared over EI, right? We said, I actually made a mistake here. That should have been in 7.5 over here. That would be 72.94 over here. And we continue until we do the very last one, which I'm trying to remember what the number was over here. 44. Until we do the very last one. So it'll be 44, that's your observed, minus your 34.44 expected squared over 34.44. So when we add up all of that together, we will get a chi-squared. All right? So in other words, we have to calculate 6 values for this table. The way in which is shown here, we actually doing every row column combination, every cell, right here. So basically, yes, colonial, yes, log cabin, yes, A-frame, that's the top row. No colonial, no log cabin, no A-frame, that's the bottom row. We have the observed frequencies from the first table, the expected frequencies from the second table. Here's the difference between them. If we square that difference, we get the numerator. And then if we take the squared difference and then we divide it by the expected value, EIJ, now we get one term of that chi-squared value, and then we add the 6 of them. I just showed you how we would have calculated that. And when we add it all together, we get a chi-squared value of 8.67. Now, to be honest with you, you don't really have to set it up that elaborate. If you know these values right here, and you've calculated these values, you can just go straight to that column right here. You don't need to do it. You don't need to put in those 2 in the middle. There's no point in doing that. But that's just to show you how it was done. But now that you have Fij, Eij, you can just go ahead and calculate this piece right here. Add them all up, and we get 8.67. So that is our test statistic right now. We must compute what the critical value is. And the critical value, chi-squared, let's put a different one, chi-squared, oh no, like this color, let's see here, chi-squared, that looks much prettier. Alpha, degrees of freedom. In this case, our degrees of freedom is k minus 1. How many populations we have? 3 minus 1 is equal to 2. Our alpha value is 0.05. So we're looking for chi-squared 0.0532. What's our critical value? So now we have to go and take a look at the chi-squared distribution. Let me see what they came up with over here. Here it is. So 5.991 is the critical value. 5.991 degrees of freedom is 2. Area in the tail is 5%, alpha 0.05. So I'm going to show you what that distribution looks like very shortly. But we get 5.991. So you can see now that 5.991, which is our critical value, is actually smaller than our chi-squared value, which is 8.67. So remember in the rules, if your p-value is less than alpha, if we could prove that the p-value is less than 5%, or if the observed test statistic is larger than the critical value, so 8.67 is larger than the critical value, we'll reject the null hypothesis. So in that case, we're going to reject the idea that the proportions are all the same and conclude instead that they differ, right? They're not all the same. So if you look at the p-value approach, so they're just showing you how they find the p-value. And I will show you this. This looks better on a diagram instead. I mean, just like a t-distribution and so on. But for now, they're showing us the area in the upper tail. And if you know how to use a t-distribution, you could use chi-squared. It's exactly the same concept. So the area in the upper tail, somewhere between 0.025 and 0.01. We're looking for a value of 8.67, remember? So 8.67 is between those two values, which means that our p-value is between 0.025 and 1%, between 2.5 and 1%. Remember, our alpha is 0.05. So since our p-value is between 1 and 2.5%, it will be less than alpha. Therefore, we'll reject the null hypothesis and conclude that the proportions differ. All right, we could reject the null hypothesis, as you can see here. The actual p-value from Excel was 0.0131. If you're doing the critical value approach, you compare the 8.67 to the 5.991. All right, so let me just show you. I want to show you the tables to see what it looks like. So I'm going to stop this share for a second. And I'm going to show you a table, chi-squared. All right, let's see here. Oops, go back here. Oh, there we go. Chi-squared. Excuse me. So as you can see, with chi-squared, as I was showing you that the distribution is kind of shaped like this, it is skewed to the right. It's not symmetrical like the normal distribution. The area, alpha, and the degrees of freedom, and the many degrees of freedom. So look at the area in the upper tail. You see an area in the upper tail? So that's our shaded region right here, and the degrees of freedom. So our degrees of freedom was 2. 3 minus 1, which was 2. The area in the upper tail was 5% because it's a one-tail test. And the one tail is always in the right, not in the left. And so with 5% and 2 degrees of freedom, we have our value right there, 5.991. That was our critical value, okay? So that's chi-squared is kind of, like I said, it kind of reminds you of the t-distribution. Yep, I didn't bother to bring up the t-distribution, but okay. So if you get that, then we're good to go. All right, so let's go back to my iPad. And reshare that. Oops. Okay, so there's one more procedure that I got to show you. And because a couple of the assignment questions might include this. Multiple comparisons procedure. Now, this is something that you definitely have to practice for to get the grasp of it. So what happens now is that in our case, we rejected the null hypothesis, right? Because we reject the null hypothesis, so we're concluding there's at least one of the means that are, proportions, not means, that are different. But the question is which one? We can't just look at them and say, oh, that one seems to be the one that is furthest away. We have to find out which one that is different from each other, the others, the most. So we have a procedure where we do the following. So first we calculate the sample proportions, right here. 97 over 135, 83 over 101, 80 over 124. Not based on the expected values, but the actual observed values. And then we compute the absolute difference between pairwise comparisons. So since we have three of them, we do 1 and 2, 1 and 3, 2 and 3. So there's only three of them. If we had four populations, we'd have to do 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, and then 3 and 4. So we'd have to do all pairwise comparisons. Calculate the sample proportions, and then find the absolute difference. So that's what we have here. So that's the absolute difference between them. All right? Now what we're going to do is we're going to compare that to a value that we call a critical value. And that critical value, depending on what it is, will tell us which of these pairs actually are significant. The pair differences are actually significant. So what does that formula look like? It happens to look like this. So when we take a pair, we will calculate this value right here, which is the standard error for that pair. But then we actually calculate this value right here, the square root of chi-squared for alpha and k minus 1. We take this value. So it will be the square root of 5.991 in this case right here. And then we would find the standard error based on those two proportions. And we call that a critical value. And what we want to do is to make sure that the critical value, if the critical value is smaller than the absolute difference, and I believe it's actually written over here. If the critical value is smaller than the absolute difference, then it's considered significance. So you see, that critical value is smaller than the absolute difference. Or I should just say the other way. If the absolute difference is bigger than the critical value, it is considered significant. Now, it might be a little difficult to appreciate this at first, but let me see if I can give you another way so that you could appreciate this. Let's go back to confidence intervals, because it's kind of what it kind of is related to. This part, which we call a critical value, is almost like a margin of error. If we're using the chi-squared to give us an estimate of our critical value, of the Z value right here, if we were doing this using chi-squared, and it's as if like we were trying to find a confidence interval based on the data that we have. And when we find that confidence interval for the difference between those two proportions, right, we have to check to see whether or not the margin of error is bigger than the point estimate. Let's just see what I'm talking about. Let's say, for example, I had a confidence interval that looked like this. 4 plus or minus 3. Notice something. So that's my margin of error right here, and that's my point estimate. So I will just make sure that I don't really care if it is negative or positive for now. So I take the absolute value. So notice that as long as this value is smaller than this one, I will have the limits of the confidence interval to be the same. So in other words, this would basically be 4 minus 3 is 1. 4 plus 3 is 7. So I'll be between 1 and 7. So both of them will be positive, which means that if this is a point estimate for a difference between, say, a PI and PJ, then it means that that difference is going to be positive no matter what. So therefore, it's significant, right? But what if I did this? What if I had 4 plus or minus 6? Notice now that the 6 is bigger. So this value is like equivalent to the critical value that we saw earlier. So this is bigger. So because this is bigger, what will end up happening is that the lower limit will be negative, minus 2 to 10. So minus and a positive. So 0 is in that interval. Because 0 is in that interval, it is possible that P1 or if PI is equal to PJ. It's also possible for PI to be greater than PJ or PI to be less than PJ. All those three things are possible in that interval. And so therefore, we cannot say the difference is significant. We could only say the difference is significant when both of the limits are either negative or positive. And the only way for that to happen is if this piece right here, your margin of error is smaller than this piece right here. That's the only way for that to happen. As long as it is bigger, right? As long as it is bigger, you're going to get one limit being positive and one being negative. But if it is smaller, then both of them will be the same, right? So it doesn't, even if I had something like, say, minus 3 plus or minus 2. The 2 is smaller, right? So if I did this, it would be negative 1. Would be, if I add it, would be negative 1. And if I subtract it, it would be negative 5. So you see, both of them are still negative because that 2 is smaller than this, than the magnitude of the 3. All right? So that's the idea behind that. So what we will end up doing with this is to calculate the CV value for every pair and then put it up in a nice little table like this to summarize it. So you calculate the PI minus P, the P bar I minus P bar J for each pair, and then the CVIJs. And then remember, if the CVIJs are smaller, then it will be significant. This one, the first one, is not smaller, it's bigger. So therefore, it's not significant. The second one is also bigger, it's not significant. But the third one is smaller. So in other words, there's a significant difference between the proportion of people who will likely repurchase for log cabins versus A-frames. And so we do have evidence that at least one is different, and we have a sense of that A-frame, likelihood of repurchasing from A-frame is very different from that of log cabin, right? But A-frame is not significantly different from colonial. Log cabin is not significantly different from colonial, but A-frame is significantly different from a log cabin. So it kind of gives us a sense of which two are significantly different from each other because we rejected the null hypothesis. And so that's the approach that would be used here. So as I mentioned to you, this problem involves a bit of computation, but once you get through it, the calculation is the same for all of them. Let me just go through the other two quickly, and then I'll work one problem, and then we'll call it a day, all right? The second one is called goodness of fit test. So goodness of fit. But just before I do that, let me just recap the important things because I need you to carry those over into these other two examples. One is that we have the hypotheses around the population proportions. Two is that our data is obtained by getting a big sample and breaking it up into rows and columns, so categories, right? And then three, we have this concept called observed frequencies and expected frequencies. Observed frequencies is what you see in your count when you collect your data. Expected frequencies is what's based on the null hypothesis. So if we say all the proportions should be the same, we'll say, okay, if all the proportions are the same, then what should we expect to see? And then we actually, we calculate those numbers and say, that's what we expect to see, but there's what we observe. How different are those two from each other? If they're not very different from each other, great, we cannot reject the null hypothesis. But if they're very different from each other, we have to reject the null hypothesis, all right? So that's that. The next thing we have to do is then to calculate this chi-squared value. The chi-squared value is what measures for us just how different those two things are apart, the expected and the observed, by taking observed minus expected squared over the expected, and then adding them all up. Chi-squared distribution is requires a parameter which is degrees of freedom, and in the case of equality of proportions, it would be what we call k minus 1 would be the degrees of freedom. All right. So once we get that, we could decide if we reject the null hypothesis or not after we've done our computation. And then we do this test if we reject the null hypothesis to determine which pair of proportions happen to be significantly different from each other. And we do that by using this procedure called Masculio something procedure. I can't even remember his name, but it's called a Masculio or multiple comparisons procedure. But it's named after someone named Masculio. All right. So we bring in some of these ideas into the next one. Goodness of fit. So what's goodness of fit now? Goodness, whereas in the first case, we just say that the proportions are equal. We don't say what they are. We don't say that the proportions are 25% or 30%, 40%. We're just saying P1 is equal to P2 is equal to P3 equal to P4, etc. In this case now, goodness of fit, we want to specify them. So we'll say P1 should be 10%, P2 should be 15%, P3 should be 45%, P4 should be whatever the rest is, right? Adds it up. So if we look at it that way, we have specific proportions. So now we could determine, if we take a big sample size, we could just multiply that sample by the proportion to figure out what we expect to get. That should be easy enough. If I say 25% of students at SMU enroll in the business school, and I took 1,000 students from SMU randomly, how many do I expect to enroll in the business school? I multiply the 1,000 by the 25%, which should give me 250 out of that 1,000 should be in the business school. So that's what I expect. But if we have, instead of, say, 250, I have a different number, then something is wrong. If instead of the 250 out of 1,000, I had 400 out of 1,000, that's 40%. So that observed frequency is different from what I expect, which is the 25% of 1,000, 250. All right? So that's the basic idea here, that we would stipulate an actual proportion and see if the data fits that. That's why we call it the goodness of fit test. So state the hypothesis. So all of the same procedures: select a random sample, assuming each is true, calculate the expected frequencies, etc., etc., etc. And we have to compute the test statistic using exactly the same formula. As you notice, same formula, Fi minus Ei. But now, because we don't have rows, multiple rows, just one row, because we have the proportions, we multiply the big sample by those proportions, we get the actual expected frequencies, and then we could compute the, we could certainly compute the chi-squared value. Degrees of freedom is the same, k minus 1. And so here we are. So we still have the same finger licks example. And let's see what we have. Example: Finger Lakes Homes manufactures 4 models of prefabricated homes, 2-story colonial, etc., etc. To help us with production planning, determine if previous customers' purchase indicate that there is a preference in style selected. So we have 1, 2, 3 types of homes. The number of homes sold for each model for 100 sales over the past 2 years is shown: 30, 20, 35. So they added a fourth one. So colonial, log, split, and A-frame. The question is asking, is there a preference between them? Now, if there's no preference, and there are 4 types of homes, so what should the proportions be? Basically, the 4 types of homes should be shared equally amongst the sales, right? In that case, each of them will get 25%. Does that make sense? So if there's no preference, they should be 25%. But if there's a preference, they should be different from the 25%. So maybe one of them is getting 40% of the sales, not 25%, 40. So a lot of people prefer that particular home. Or maybe one of them is getting a lot less, say only 5% of the sales, so people don't like that particular home. So in this case here, even though we were not told that it was 25% each, but from the problem statement, because we're saying that they want to determine if there's a preference between the styles selected. So you have to then say, well, if there's no preference, then what does that mean for proportion of sales? Each of them should be equal, which basically means 25%. Now, in the first case, we did a testing for equality of proportions, but we didn't know what the value was. In this case, we're testing for equality of proportions, right? And we are then assuming that they all would have a value of 25%. So in that case, we have 30, 20, 35, and 15. So if we're talking about 100 homes, each of them should be 25. But that 25 is different from that 30. That 25 is different from that 20. That 25 is different from 35. That 25 is different from the 15. So maybe there's some preference here. 35% of the homes are split level, or maybe people tend to prefer the split levels, right? Not so much the A-frames, 15%. So our null hypothesis, notice, will state that the proportions are all the same, 25%. Or they're not all the same, and we don't need to stipulate what they are, but just saying, well, they're not all the same right here, all right? They're not all the same. And then we have it labeled C for colonial, L for log, S for split level, A for A-frames. Degrees of freedom is K minus 1, so 4 minus 1, which is 3. If we're testing at alpha is 5%, so if 0.05, 3 degrees of freedom, we could go to the table and see that this is 7.815. So that's our critical value. So if our chi-squared value is greater than and equal to 7.815, we will reject the null hypothesis. So we have the observed frequencies already, which are those values. Those are our FIs. Now we need our EIs. Well, the EIs are easy because it's just simply the proportions multiplied by the 100. So the EIs will turn out to be 25, 25, 25, 25. And to calculate the chi-squared value, we'll have to do F minus E squared over E. So it'll be like 30 minus 25 squared over 25 plus 20 minus 25 squared over 25, right? Plus 35 minus 25 squared over 25 plus 15 minus 25 squared over 25 equal. So that's how you calculate your chi-squared value. All right, let's see what that turns out to be. So it's all done here for us. Turns out to be 10. Remember, the critical value, chi-squared critical, was 7.8 something, 15. So as we can see already that 10 is larger. So it seems like it's suggesting that there will be a difference between, in other words, those proportions do not line up nicely with the 25% each in this case. All right? So if we wanted to find p-value, and since we're looking for a value of 10, the value of 10 is between here and here. So it's between 2.5% and 1%, 1% and 2.5%, which is smaller than 5%. So we will reject the null hypothesis in that case. All right? So again, you saw that I've demonstrated that it is the same kind of calculation. We just need to be able to stipulate the right hypotheses. Right? We just need to be able to stipulate that. So that was number 2. And the third one now, the only difference between the first and second and the third one is that the third one now could have more than 2 or more columns and 2 or more rows. You're not limited now to when you're doing, say, the goodness of fit test, you basically just have 1 row. When you're doing the quality of proportions, you just have 2 rows. But when you're doing test of independence, you could have multiple rows and multiple columns. I gave you the example with gender, male, female, type of sport, baseball, football, soccer, basketball, baseball. Oh, they both are ball, basketball, and both baseball, BAS. Well, you know what I mean. All right. So here we have 4 categories of sports, for example. Maybe we could even put curling in there, and or swimming. And then we have male and female. So we have 2 this way, but then we have 4 that way. So that's a 2 by 4. But we could also have, if we wanted to change it to, say, age now, we could say young people, then we could say adults. When I say adults, like, we best put age ranges. We could say less than 25, then we could say here 25 to 50, and then over 50, 50 plus. That's 3 categories now for age, if we wanted to, right? Where you could call people more like, you know, young folks, sort of middle age, and then old folks. All right? So in that case, this is what we have. And the analysis is identical. It's just that we must now stipulate the hypotheses appropriately. So since we're testing for independence of 2 categorical variables, in this case that I just mentioned here would be that the type of sport and people's age are independent versus they're not independent. So you see here, the column variable is independent of the row variable. Column variable is not independent of the row variable. But those things have names. So we could actually put it in context. So we'll be talking about the age and preference for type of sports related versus they're not related. That's kind of the context we would put in here. All right. Test statistic, notice, is the same thing as the first case. So what is observed, what we actually have in the data, what was expected, exactly the same way, row total, column total, right, over the grand total. So you're using the very same examples with the homes again now. Let's see what our data looks like. So now we're taking the number of homes sold for each and the price in the past 2 years as shown. So we're looking at 2 different price categories where less than 200,000 and greater than 200,000. And 18 colonial homes sold under 200,000, 6 log homes, 19 split, 12 A-frame, and then over 200,000, 12, 14, 16. So those are our observed frequencies, right? We would have to calculate our totals over here, row totals. So for example, 18, 6, 24, 24 and 12 is 36, 36 and 19 is 36 and 19, 55. And then we have 19 and 14 is what, 33, 33, 45. So that's 100 homes. And then that's 15 A-frames was sold, 35 split levels, 20 logs, and 30 colonials. And those should add up to 100. So your column totals should add up to the same, the column totals, when you add them up, they should give you the same value right here. So 55 and 45 give us 100, and those give us 100 as well. So those are our observed frequencies. Now we have to go and calculate the expected frequencies, which is the same row total. So if I want to calculate this one, the expected frequency here for colonial and under 200,000, I would say, what is my row total? My row total is 55. What's my column total? 30. What's my overall total? 100. So it would be 55, times 30 over 100. The next one here would be 45 times 30 over 100, etc., etc., etc. So once we calculate all of those would be our expected frequencies, and then we now use that formula to find the chi-squared. So here's the setup. Price of home is independent of the style of the home. Price of home is not independent of the style of the home. So here it says expected frequencies, but those are not the correct expected frequencies. Those are wrong. Because 18, 6, 19, 12, let me see that, 18, 6, 19, 12. Those happen to be the same as the observed. They have to actually calculate that. And let me just tell you what, so for example, what that should have been, that 18 for expected frequencies should have been 55 times 30 over 100. What is that? 55 times 80 of 30, divided by 100. 16.5. That should have been 16.5. So there's an error here. And they have to add up to the 30. So that's 16.5, 14, 13.5. Then we could see a 55 times 30 times 20 over 100. 20 times 55 divided by 100 equal to 11. So that should be 11. And if that's 11 and that's 20, that will be 19, because the two of them must still add up to 20. 55 times 35 over 100. $19.25. So that's 19.25, which basically means that this is out of 35, so 16, 15.75, because they must add up to 35. And 55 times 15 divided by 100, 8.25. So that's 8.25 and must add up to 15. 7 and 8 is 15, so it's 6.75. All right, so those values in blue are the expected frequencies. Whoever made those notes actually recopied the table but did not change the numbers. So now that you have that, the expected frequencies, if I had to now go ahead and calculate, not the expected frequency, but the chi-squared value, I must now take 18 minus 16.5 squared over 16.5. And then I must repeat that. So I must have, how many of those? 8 of those values. I'll do 2 more. 6 minus 11 squared over 11 plus on the very last one, 3 minus 6.75 squared over 6.75. And that will give us a chi-squared value, whatever that is. It turns out to be 9.149. That's what we get right there. So you notice how they have the right expected values right there, 16.5, 11, 6.75. But what they showed in the table were not those values. Anyway, once you calculate that, that's your test statistic. You can find your p-value, because now, the degrees of freedom in this case is different. It's given rows minus 1 times columns k minus 1. Row minus 1 times columns minus 1. So if, in this case, we just have the 2 rows, so that's going to be 2 minus 1 is 1. So it will still be just column minus 1. And if we're talking about 5%, it's going to be 5.991, the same value that we had before. So in terms of our chi-squared values, 9.145. What was our alpha value? 5%. So, so we have 2 minus 1 times 4 minus 1. You see here, row minus 1, k minus 1, and then that gives us 3. So 3 degrees of freedom and 5% alpha give us a critical value of 7.815. But look at our chi-squared value, which happens to be bigger. So we will reject the null hypothesis. All right? For the p-value, we look up the 3 degrees of freedom for chi-squared. We'll find that 9.145 in between here, which basically means that our p-value is between 2.5% and 5%. It's less than 5%, but it's bigger than 2.5%, which means it's still smaller than alpha. We'll reject the null hypothesis as a result. And that's it. The actual p-value, if you're using Excel, would be 0.0274, but we don't have Excel in an exam situation, so we will have to use the inequality when we're using the tables. All right. And then if we're doing the critical value approach, we'll compare the 9.45 to the 7.815 and reject the null hypothesis. We would conclude, therefore, that we have sufficient evidence that the type of home is related to, and the price are related. The type of home and price are related. I believe that's what we set out to test. Let's just go back to the hypothesis again. The price of the home is independent of the style. Price is not independent of the style. So it turns out to be that they're not independent of the style. Style is related to price because we rejected HO. Okay? So that brings us to the end of that particular chapter. I think what I'm going to do, rather than try to work that example for you right here, I'm going to do it as a separate question just by itself, upload it to YouTube and share it with you. We've now crossed 2 hours and 13 minutes, and I'm sure after a while it's kind of difficult to have a sort of a one-directional conversation for more than 2 hours. So I think the best thing to do then, if we understood those principles right here, is I will take the examples that I have put together for you, and then I will have it. I basically was one additional example. I was going to do one that is a test of independence because it has all the same calculations as the goodness of fit test and the equality of proportions test. So those three, remember, those three things use the same concept of comparing observed frequencies to expected frequencies. And the expected frequencies are determined by the null hypothesis. So if the expected is very different from what is observed, we reject the null hypothesis. If it's not very different from what we observe, we don't reject the null hypothesis. All right? So that's the basic idea behind it. And if we grasp that concept, then we should be able to just work with the formulas that we're given, which is the formula for the expected frequencies, row total times column total over the overall sample size. If you use that and you calculate the chi-squared value, remembering that the chi-squared distribution is used just like the t-distribution, you'll be well on your way. All right? Now, I should mention, I do believe analysis of variance is probably the toughest chapter of all of those, what we have to do. So chapter 13 is important. It's very important if you want to get the lecture that I have videos pre-recorded for analysis of variance that you try to watch some of those videos before you come to our next class. And then that would help to make it a whole lot easier to follow along. If you have a chance to preview any of the videos, I know I didn't have one for chapter 12, but if you have a chance to preview videos before coming, it would help to make what we do here a lot easier, okay? So on that note, if you have any quick questions for me, please shoot. If not, we'll call it a day, and then I will post a separate worked example for you as soon as possible. Remember, I'm going to make myself available for an hour on Thursday if you have any questions, like office hours kind of a situation. Okay? So good. Any questions?
I don't have any questions. Thank you for your time.
No
My
problem.
phone's about to die, so I'm gonna run.
Okay, no problem. Understood. And I'm going to be posting the video of this class so that you have a chance to watch it again. So
Okay.
the links to all the videos are actually posted. I actually deleted some of the early ones, but I'm actually going to upload them via YouTube because this program that I'm using, Zoom, gives me only 1 gigabyte of cloud storage, and I was storing them in the cloud, and I don't want to increase my capacity and pay more for subscription. So rather than do that, I'm going to just download the videos and then I'm uploading them back on YouTube for free. So I will provide the
And for test number for our second test, will it be basically on? Will it be for 14, 13, and 12, like 10 to 50, 10 to 14?
It will exactly. It will be that. It will be,
Yeah. Okay.
and I know that it doesn't cover regression, so therefore it will be 10, 12, and 13. I don't think we're going to cover
Yeah.
regression by that time. Yes.
12. Yeah. So 10, 12, 13, and 14 as well, or no?
No, 14 is our very last chapter, so
Okay.
it will not include chapter 14, which is regression analysis now.
Okay. Perfect. Yeah. Chapter 13 is pretty big.
It is a big chapter.
Yeah.
Okay. All right, great. So take care
Thank
then.
you.
I'll see you guys on Thursday, if not next week, Tuesday. Okay?
Okay, thank you.
Okay, good night. Have a good night. Okay, bye-bye.
Good night.
Okay.
Good night. Thank you.
No problem. You take care.
You too.
Bye-bye.